Okay, so we're going to start running through some of these problems with force in them. So this is going to kind of take us through this process that I'm displaying right here, where we're going to draw a free body diagram, make the XY chart, fill in the positives, negatives, zeros for the directions, find any specific values based on information that's given in the problem, and then use any trig if we need to, if there's anything at an angle, and then find anything that's missing, and then net force and the acceleration. So, this first problem we're going to go through is just the first one on the practice problems. I've posted all the answers to these as well, so you can look at these on D2L. Kind of written out. I haven't explained them. I'm going to go through the first two actually. So let's start with this one, and then I'll leave the last two for you guys to look at on your own. So let me talk about what's going on here. So this one reads: a man pulls a box, a 50 kilogram box. So anytime there's a number, that's important. So a 50 kilogram box at a constant speed. This is a really, really important part. So if you ever see that, like make note of it. Constant speed is really important. He applies a 200 Newton force at an angle of 30 degrees. So they give you another angle, they give you a force. And it says draw a free body diagram. So the free body diagram, again, is just a dot. So you're gonna draw a dot. And then you're gonna draw the forces that you think are acting here. So if we draw our forces, I would say there's a force going up and to the left. And I'm gonna label that tension because it looks like he's pulling on this with a rope. And if I wanted to, I can write in theta or 30 degrees here just to kind of be specific about what's going on, okay? So I want to get rid of that line. So that's, yeah, okay. So we got our tension at our angle theta. So that's something we're gonna need. Okay. So so there's our tension. What other forces are acting here? Okay. So he's pulling down, or he's not pulling down, but gravity is trying to pull down on the box because it's pulling downward. There's also a normal force, and what happens a lot of times is people automatically draw an arrow going up that's equal to the gravity, and I don't think it's going to be equal because he pulls up. So if he's pulling up, some of that pull going up is going to take away some of this gravity, and the floor just has to provide as much as it needs to. So the normal force, again, adjusts, and we talked about that in the lesson with the normal force. So this is like pushing up from the bottom. And then finally, it doesn't say that this is a like smooth or frictionless floor. So there's going to be friction, and if the box is sliding at a constant speed, it looks like going to the left. So I would say the box would move that way based on his pull. Friction is going to go the opposite way. Okay, so there is a basic free body diagram. Again, I'm not getting out a ruler and checking to make sure you have the exact right size or a protractor to get the right angle. But you should have the general direction correct, and you should have the general size of the arrows correct. Okay, so next step we're going to do is we're going to make a table. So I'm going to try to do this a little bit nicer than what just my hand drawn, because yeah, my handwriting is not very good. So all right, so so we got our chart here. I'm going to need a horizontal row for every arrow that I drew there. So I got 4 arrows, so I need 4 rows. And then I'm going to need one at the bottom for the net force. So oops. More here. There we go. Okay. So I'm going to start filling in X's and Y's. And I'm just going to list out the forces that I have. So I have gravity. I have the normal force. So that's good enough for those. So I can get the next one. I have friction, or I have the tension. We'll do the tension next. So the guy pulling, I have friction. And then finally, I have the net force. Okay, so that's the bottom box here. All right, so let's try to fill in the positives and negatives and zeros based on this free body that I just drew. So, okay, so let's start with gravity. So gravity, and again, you have to do this step. This is just as important as doing any of the math steps. Figuring out what's positive and negative and zero is vital to doing the problem. If you don't do the problem this way, you're going to make mistakes. So gravity is pulling down, and that's in the negative and the y. So I'm just going to put a little negative sign there. And then it's not going left or right. So if it's not going left or right, there's nothing in the x, so that's a 0. Hold on one second. So we got 0, we got a negative here for gravity. For the normal force, we're gonna talk about the normal force here. So the normal force is going up, so that's positive in the y. And it's not going left or right, so that's 0 in the x. So I've got those two filled in. For tension, it looks like it's going left because it's pulling to the left. This guy's pulling to the left, so that's going to be negative in the x. And it's going to be pulling up as well, so that's going to be a positive here in the y. So that's got two components. That's one of the ones that's special. And then the friction is going to the right because if the box is sliding to the left, friction is going to go to the right. And friction is not going up or down, so this is going to be a 0. Now, this next step comes from this description up here where it says it's at a constant speed. So constant speed, vital to understanding this. Constant speed means that it's not acceleration. So it's not accelerating. So there's no A. And if there's no acceleration, that means that all the forces are balanced or the net force equals 0. So if the net forces equals 0, that means that both of those boxes in the bottom of the chart are 0 because, again, if we think about our situation, it's balanced. So this is a balanced situation. Everything is canceling out if it's going to be able to keep moving at a constant speed. That's Newton's first law. So this is 0, and this is 0. So that's good. That fills in a lot of information. Okay. So now I'm going to make the x and y components for the applied force. So I'm going to try to find the x and y pieces. So the only thing that has an x and a y is tension. So I'm going to find tension in the x and tension in the y. So tension in the x is just going to be t cosine of theta. So the tension force, if we go back up here to the problem, says that it's being applied at 200 newtons at 30 degrees. So it's going to be 200 cosine of 30. 200 cosine of 30. And that, if you put that in your calculator, gets you 173.2. It might not be exactly 173.2, might be rounded, but that's just, you only have to go one decimal. For the next part, it's going to be 200, or sorry, t sine of theta. Write out the step for you guys. And that's 200 sine of 30. So if I do 200 sine of 30, I get 100. And those are the numbers that I'm going to put in for my x and y. I've already filled in the negative and positive. Those are just going to stay there. Your calculator is always going to give you positive values. So you got to make sure that you get that negative and positive. And that's why I'm saying it's just as important to do that step to get it to work out. Okay. So I've gotten those numbers and they're in the correct boxes now. So I've gotten the pull or the tension in the x and y. It says to calculate the missing forces, so gravity, normal force, friction. So let's do gravity first, because gravity's got a really simple equation and we can kind of plug into it. So G equals mg. So m is the mass of the box. So if we go back up here, the mass of the box, it said pulls a 50 kilogram box, so that's m, because kilograms measures mass. 50 times 9.8. So 50 times 9.8. Put that in your calculator, you'll get 490. Again, your calculator is going to tell you that it is positive. We are deciding up here that it's negative because gravity is pointing down. So 490. Okay, so I think we have everything that we need to get the rest of the information. So friction, if you said, okay, well, let's try to solve for friction, because I know there's an equation for friction. F equals UN, right? So F equals UN. They didn't tell us the coefficient. They didn't tell us how slippery the surface was. We don't know the normal force yet, so I can't figure out F from this equation yet. If I had this information, I can just go ahead and plug in, but we're gonna be able to do it a different way. So after you've kind of gotten each chart or each column in the chart so that there is just one missing box, you can solve for that missing box just using the rest of the math. So sometimes it'll be the bottom two boxes that you're looking for. Other times it'll be boxes in these pieces. So if I'm taking this and I'm just adding this all together, so 0 plus a negative 173 plus whatever this friction is should get me 0. To balance this out, to make it get to 0, this has to be positive 173.2. So that is my friction force. And then for the y, I have negative 490 plus some normal force plus 100 plus 0 gets me to 0. So like, this is really just like a big kind of, you're just adding all these forces together in their X and Y components to get to the net force on the X and the net force on the Y. And we said that because it's a constant velocity, everything's balanced, so these are both zeros. So to make this balance out, this is negative 490 going down, I need a positive 490 going up, and this is this tension is only 100, so the normal force has to be 300. So, and 90, sorry, so 390. So positive 390 is my normal force. So I have all my individual forces that are acting on this boxes. Oh, unit-wise, these are all newtons. So all of these things in this chart are all newtons. So you could write newtons everywhere, or you can just write an N and draw an arrow like I am doing, okay? So on your test, when it asks for units, just draw the normal, or the N for newtons with an arrow. All right, so the last step here, there's a couple things here for 4. It says calculate the coefficient of kinetic friction. So that's this U. All right, so we're gonna look for U, and we're gonna use fun. So that equation, F equals U times N. And we know the friction now is 173.2. U is what we're looking for, and then N, the normal force we just said, is 390. So we have everything that we need. We only have one variable missing, so we're just going to do the algebra and solve. So U is equal to 173.2 divided by 390, and that value is something like 0.44. So again, a decimal is good. It's between 0 and 1, so it seems to make sense. For the coefficient of friction, there is no unit. That's something I forgot to talk about before, but it's just a ratio of newtons divided by newtons, so it's unitless, okay? The acceleration of the box, we answered this very early on. The acceleration of the box is 0, and net acceleration 0. And that's because then it's balanced. Again, it's a balanced situation. The net force is 0. So if these are both zeros, that means if we plug into F equals ma, if the force is 0 and the mass is 50, which we got here, we could do the math here and solve for A. But if you have no force, you have no acceleration. So no net force gets you no net acceleration. Okay, so another way you can talk about it, it's going at a constant velocity. So if you have a constant speed, constant velocity, that means that you cannot have an acceleration, because if you had an acceleration, it would change the velocity. So that's the first problem. The second one's a little bit easier. This one talks about a helicopter. So it's just in one direction here. So I'm going to take you through one that's in one direction. 3 and 4, they're pretty good problems. They're similar to the one that we just did. They might ask you to do some things differently, or they might ask you to kind of do a little bit more. So I would just go back and look at those answers and try to follow along and see if you're getting it. If not, I can make another solutions video for those, and maybe I'll do that. I don't want to make it too long. So let's go ahead and do this one, and then we'll talk about the friction simulation, and I'll make another additional video for problems 3 and 4. So for this one, a 4,600 kilogram helicopter, so again, that's the mass, that's M, accelerates upward. So now we're accelerating. So that's the net acceleration, that's A. And wants to determine the lift force exerted on the propellers by the air. So we're trying to figure out the lift. Drawing a free body diagram for a helicopter, it's pretty simple. So you got the helicopter here. You got gravity trying to pull down. All right, but the helicopter is actually moving up. So the force going up should be greater than gravity. And I'm just going to call that lift. And you could just call it push or pull or whatever you want to call it. It doesn't really matter. Applied force is fine. But you have these two forces, but the lift is bigger than the gravity force. So there's my free body diagram. We're going to make an X and Y table. So I'll do this really quickly. If you notice, is there anything going in the X direction? So are there any forces in the X? And again, you get the forces in this chart from just your picture. So we got the lift, which is going up. So it does not go in the X, so that's 0. And it's positive in the Y because it's going up. For gravity, that's the other force that we have. It is not going in the X direction because gravity pulls down, which is a negative. And those are the only two forces, so that's it. So the net force, if we have 0 and 0, and you add them together, because again, this is just basically just addition, so you just add the columns. So 0 plus 0 gets you 0. So there is no net force in the X. So we didn't have to worry about that, okay? For this box here, we're going to need to use our acceleration. So the net force is equal to the mass times the acceleration. So we're going to be able to fill that in and figure it out. So we're looking for the lift. That's going to be our thing that we're solving for. So I'll put a question mark there. Gravity is just going to be m times g. So let me type that out. So the gravity force is m times g, and this is b down here. So and the mass was 4,600. Multiply that by 9.8, and that is 4,580, and that's newtons. So that's going to go in this gravity box. So -45080. So that's that one. For the acceleration, we have the acceleration and we know the mass, so we can figure out the net accelerator or net force. Excuse me. So the net force is equal to m times a. So it'd be the 4,600 times 2. So 4,600 times 2 is 9,200 newtons. And this is going to be a positive, and I write out positive, but why do we know it's positive? We know it's positive because it's going up. Like it's as simple as that. So it says it accelerates upward. So that's a positive acceleration. So it's a positive net force. So now you can see that we have one missing box, and that's where we're good to solve. There is no equation for the lift force that we know of. So we're solving for this mystery box here through some kind of equation. So again, some number minus or plus a negative 45,080 gets you 9,200 extra. So like if you want to just make this a variable L, sometimes people get confused how I solve this, so I'm kind of writing it out. So L plus a negative 45080 equals 9,200, and I put a positive 9,200. So if you kind of look at this, you just say, okay, I just have to do algebra here. This isn't rocket science algebra, so I just take that negative to the other side, it becomes positive. So L would equal, and let me type because again, my handwriting is not good. 9,200 plus the 45080, and you should get something like 54,280 newtons, and it's going up. So that's it. That's problem number 2. Pretty simple, only one direction. But again, you can kind of see how sometimes you have to use F equals ma and put it in that box. Gravity is pretty straightforward. You just use that. And then we have to do a little bit of algebra to kind of figure that out. So sometimes people will try to subtract those two and they'll get an answer of like somewhere around 44,000 or 43,000 newtons. That wouldn't make sense. So like 44,000 minus 4,500 wouldn't get you 9,200 and 9,200. So make sure your answer makes sense at the end and that you're doing it correctly. All right, so let me jump ahead. I'm going to come back and I will talk through these two problems on a different video at the end. But I want to talk about this lab that you're trying to do. Okay, so let me minimize my face here. So you're going to be doing a friction simulation lab. And the friction simulation lab, I think really does give you a decent insight into kind of the difference between static friction and coefficient friction. So you're going to fill this out and submit it on D2L. But what you're going to do, the directions are all on the page that's already posted. But you're just going to go to Google, go ahead and Google PhET, P-H-E-T. That's the University of Colorado at Boulder. They have a lot of simulations there that we'll be using throughout the semester. And you're going to Google PhET Force and Motion Basics. It'll be HTML5, so it should run on any platform. And you're going to, it comes up and it has all these different options. You're going to click on friction. So I screenshotted what you want to highlight, and you're going to click on that. It's going to bring you to this screen down here. So you're just going to follow directions of the lab sheet. One thing that can confuse people, FA on my lab sheet is the applied force. So that's like how much you're pushing. So the applied force in this picture when I screenshot it was 95. The friction force was also 95. So you're just going to follow directions. It tells you to click on various boxes over here. What you're going to do is you're going to increase the applied force that you are pushing with this robot. So you're going to increase the force. Eventually, you will overcome the static friction and the box will start moving. And really, there's a couple different parts here. So the first one is to try to figure out what is the maximum static frictional force. So you're going to push on it until it moves, and then you just basically go back one, and that's the maximum static friction that it can apply. After you get it moving, You're going to figure out how much kinetic friction force there is. So like what you would have to apply to keep it moving at a constant velocity, and you just follow the directions on that. And then on the back, it asks you to vary a couple things. So you're going to like move a refrigerator on top of the crate and make the normal force bigger. So you should kind of understand what's happening there. You're going to push it so it's moving, and then stop applying a force. So you'll like push, 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 and then you'll make this go to 0, and the box will just slide away from the robot. And you're asked to kind of look at the speed and decide what's happening. So it goes into enough detail that I think it'll help you. You're using like coefficient of friction. You're doing normal force. You're doing the friction equation fun. So all those things are good. Again, drawing free body diagrams will definitely help you, and trying to remember if it's a balanced situation or an unbalanced situation. Okay, so I'm gonna stop there. I'll go back and make another video for 3 and 4, and these are all just kind of more pictures of the other thing, of the lab. So we'll catch back up, and we're almost done with section or lesson 5.